All right, so this lecture comes in the continuation of the lecture on Tuesday where I talked about the beginnings of programming in the form of the Turing machine and what it meant to program those machines. That, if you remember what I said, it's basically the concept of programming that emerged from that model of computation was that a machine, a computing machine, is a machine that has some capabilities of operation. So you can do certain operations on that machine. And what programming is about is specifying the sequence of operations of that machine. That's what it is. So do this, do that, move left, move right, read, write, things like that. And so that is pretty much the beginnings also of the imperative programming style and this model that there is a machine that has a number of possible actions that it can do. And what programming is all about is we have our higher order abstract concepts that we want to achieve, like mathematical functions, whatever, and it's up to us, the human programmers, to specify, to break down, to basically map from the higher level goals to the exact sequence of operations that the machine should do in order to achieve that goal. Okay, this is where the whole field of algorithms comes from, which is that basically the algorithm is a way, okay, given the mathematical function, something that we want to achieve, that is specified in mathematical terms very nicely, just as the what we want to do, right? How do we make the machine do that, right? What is the process? What is the sequence of operations that makes the machine do that? So today I'm going to talk even more about the elements of imperative programming style beyond the Turing machine. And it evolved way beyond it, and we see elements of imperative programming now in pretty much almost all the languages that you guys use. So a lot of things that I'm going to talk about, some of you may already know, for some maybe a refresher, for some of you maybe something that you kind of picked up somewhere, but you never really had a formal presentation about it. So all of this is going, what I'm saying is that this lecture is all going to sound very familiar because I'm talking about imperative programming, which all of you are familiar with, even if you have never had a formal lecture about imperative programming. So I'm going to talk about the machine model for imperative programs, structured versus unstructured control flow, and assignment, which is an interesting and very critical and central element of imperative programming, and talk a little bit about variables and names. So to understand what is going on in those imperative languages that you all know. So what is imperative programming style? That is basically the idea that there is a flow of operations, a sequence of operations that we need to control. And so that's the control flow. Right? There's these statements, and now it's up to us to figure out how to sequence those statements and how to control them, given that at some point there may be several options about what to do. And the key operation in imperative programming style is the assignment. The assignment, what that means, coming from the Turing machine, the assignment is literally replacing a value somewhere. Okay, so the fact that the Turing machine, you can overwrite, so basically you can, if there's something there, you can overwrite that cell, okay? That is the physical representation of an assignment, okay? An assignment is changing the state, destroying something. I'm going to already start bashing about, by talking bad about assignments, because basically assignments destroy things. Assignments destroy information. That's what an assignment is. And towards the end of the lecture, we'll talk a little bit more about the semantics of assignments and the syntax of assignments, that it has slightly different semantics on different programming languages, even though they all kind of converge to use the equal sign for assignments these days. But in different languages, actually, the equal sign does not mean the same thing. And in particular, some languages that you may No, okay, there's subtle differences between the meaning of the equal sign. So, but basically this, what's called a side effect is that if something gets destroyed and something new gets placed there. So history gets destroyed, okay? And that is very much sort of a key element of imperative programming is the fact that there is the concept of state, and the state gets updated and the old state disappears. And in particular, this will become, the reason why I'm kind of stressing this very much is that when we go into functional programming ideas, this gets revisited entirely. Okay, there's no concept of assignment at all, and nothing ever disappears. So, as I said, the oldest and most popular paradigm comes from the Turing machine, made it to Fortran, which, by the way, I don't know how many people know how old Fortran is. Can anyone type in the chat your guess for how old Fortran is? When do you think that Fortran was created? Yeah, 1950s, Aditya. That's right. Actually, it was even a little earlier. Fortran is one of the oldest programming languages. I mean, it was almost started being designed almost when the first computers came around in the late 40s. It's quite remarkable. Algo, C++, Java, C#, you name it, and even, you know, all the languages that we use, the most popular languages, they all have imperative programming elements, even the ones that are more functional. So assignment mirrors computer architecture. So the idea is that in a von Neumann machine, there's and I'll explain a little bit more. I think I have yeah. Okay, so let me explain a simplified model of a computer machine that is based on the von Neumann architecture. This is basically a very simplified version of the von Neumann architecture. So on the left, you have sort of the very short-term memory in terms of registers and things that are very easily accessible, very fast. There's some sort of a register that holds the program counter. So the left part I'll just point to, but let me start with the middle part, so the code. Okay, so there is supposed to be a part of the memory that holds the program, right? So that's what I was talking about in the other lecture. This had to be invented, and this was the big invention by von Neumann. Is this idea that you can store the program as specification of the operation of the machine. You can store it externally, and then when you need to run it, you load it. And so there is a part of the memory that holds the program. And so that part of the memory, as the program is executing, you need to know where you are, right? So that's where the program counter, that little register program counter here. So when you execute an instruction, then you move to the next instruction, and then you move to the next, unless it's a branching instruction, some sort of a conditional, and then you do big jumps. That program counts as those big jumps. So there's the code. So it's a part of the memory that holds the program. And then the rest of the memory holds the data of the program. So and typically, the data part of the memory is divided in two types of memory. There's the stack and there's the heap. And I'll tell you the story of this. So even if you already know about this, because you learned, in computer engineering or something, I can bet that most of you don't know the history of stack. Let me try to ask you something. So when do you think that stacks were invented? They had to be invented, by the way, for computers. 40s, 30s, 50s, 60s, 70s. What do you think? Okay. So there's actually one paper that that is the paper that introduces stacks for the use that they're being used right now. And that was a paper by Edgar Dijkstra. Maybe some of you have heard about him. He's another famous old computer scientist, Dijkstra. And it was a paper that he published in 1960. Let's see if do I have it here? Yeah, no, I don't. I have that paper somewhere. I don't know why I don't link it from here. Is it this one? No, it's not this one. It's not this paper. It's another paper that he wrote explaining stacks. Now, first, let me tell you, let me talk a little bit about the stacks. This is an interesting piece of history because all of you probably have seen stacks, especially when you get the Stack Overflow, right? You've done, so you know the site Stack Overflow. Many of you already know that the reason why that site, you know, the name of the site is meaningful is because Stack Overflow is the kind of error that you get when you run out of stack memory. That sometimes can happen when you have sort of an infinite recursion kind of thing, right? That you just basically you start having call after call after call, you never return, and you run out of stack, right? That's an interesting and very popular way of erroring in programs. So first, let me tell you what is the stack. For those of you who don't know, I think at least half of you probably know what the stack is, but let me tell you what it is. The stack is a piece of the memory, okay, that is used to keep track of where you are in the sequence of function calls. So suppose, you know, your program starts in the main function, right? And then the main function calls another function, f, right? And then that f calls another function, g. And then another function, g, actually calls f again, right? So that sequence of function calls, in order for the program, in order for the machine to be able to track where you are, there is this basically a stack, which is a data structure that is first in, last out, as you probably know from algorithms. That, you know, you call a function, there's some piece of information that gets placed on the stack. That function calls another function, there's another piece of information that gets put on top. And then when you return, the last one from where you return gets popped out of the stack, right? So in this way, the machine that is running the program always knows where you are and where you should return, right? So the famous stack as used in machines, right, for run programs, is a first in, last out data structure that is used to keep track of where you are in a sequence of function calls. Okay. Now, this is, okay, you probably have seen the stack data structure in your algorithms course. You probably heard about the ways that stacks are used in virtual machines, like, you know, in machines that run programs. What you probably don't know is why, right? And the reason, when did it start and why did it start, right? Why do we have stacks? Well, the way that these machines run programs before, so in the 40s and 60s and 50s, before the stacks kind of came around, the code, so if you had there were already the concept of subroutines, okay, in the 50s, Fortran already had subroutines, some sort of a function thing, right, some modularization. And so the way that you would lay it out, the subroutine in a piece of the memory and another subroutine in another piece of the memory, right? And so when you called, when this one called this one, you would just jump over there, and then you know, you needed to know where to go back to. Okay, so you needed to know where to go back to, where to return. Okay, and that piece of information of where to return was something that was kind of not very easy to track. You had to manage the return, right? Where were you called, and how are you going to go back there when the subroutine is over? And not only that was that hard to manage, but to make things even more complicated, if your language allowed recursion, right, meaning that the function inside the body of the function could call itself, then that was super confusing. Like, how would you keep track of how many times did you call the function, and how would you what would go back mean, right? When you added recursion into the mix, people were very confused about how to implement recursion. In fact, throughout the 40s and 50s, the programming languages could not express recursion. Okay, the way that the programs and the programming languages were implemented, they couldn't figure out how to implement recursion because they couldn't keep track of this idea of a function call. Right? They had functions, and the functions were occupying space in memory, but the dynamics of the call was something that they weren't really they hadn't figured out how to track that, the dynamics of the function calls, right? And so it was the need to track function calls dynamically that Dijkstra came to this idea of using the stack data structure to track, right? It's a good data structure for that kind of purpose, right? It's, first in, last out. So that's where the stack comes from. And the stack comes from the need to be able to implement recursion, and that was something that was necessary for some programs. Okay, so all right, so we have the stack, and that's the reason why so the stack is typically a limited part of the memory. It's not infinite, it's limited, and you can either say at the start of the virtual machine, you say how much stack you have, or in Python, for example, there's a function that you can set. You can also specify how much stack you have, how many recursive calls you can have. That sometimes is configurable, other times it's fixed, but in any case, it's always limited. And so if you have a program that, for example, is doing recursion, lots and lots of recursion, millions of times, eventually you run out of stack memory and you run into the Stack Overflow famous problem. Okay, so the stack is a piece of memory that is used by the machine that runs programs for tracking function calls. Okay, the sequence of function calls. That's a really important technology that was invented by Dijkstra. Actually, it was not invented by Dijkstra. Okay, let me tell you a little bit of history. He was the one who made it famous, and I guess because he was here in the United States and a lot of the work in computers was happening here in the United States, he got famous for it. But there were other people in Europe a couple of years earlier who had come to the same conclusion that they needed some sort of this kind of data structure, first in, last out data structure for tracking the sequence of subroutine calls. Okay, so Dijkstra was the one who made it famous, but he was not the first one. All right, so there's the stack, and then there is the heap. Okay, and this is where things sometimes gets confusing because the stack, computer science is full of confusing things, words. Lots of people use the same words for meaning different things. So in this case, thank God, the stack means the same thing. You have the stack data structure that you studied in algorithms and data structures, and the meaning of it is pretty much the same here. It's just the use of the stack for the purpose of running programs. The heap already, however, has a completely different meaning. You also have a heap data structure. Okay, if you studied algorithms and data structures, you probably came across a heap data structure. Okay, it has nothing to do with the heap in virtual machines, or in machines that. I'm sorry, I'm using the term virtual machine to denote machines that run programs. Okay, you can call it computers, but virtual. I'm going to call it virtual machine. So the heap, you probably also heard the word heap, for example, associated with, for example, Java. Like in Java, you can start it with a certain size of the heap. Yeah, everybody heard about the heap? Yes. Okay, so this has nothing to do with the heap data structure. It couldn't be further from it. There's absolutely nothing to do with it. In the virtual machines, the word heap literally just means a dump. Okay, it's a piece of memory that is going to be used for storage of stuff, okay? And the way that that storage is organized depends entirely on the programming language, on the implementation of programming language. So Java has a very particular way of managing the heap. Python has another particular way of managing the heaps. Every different language has a different way of managing the heap. But what they have in common is that they have a heap. And the heap is a piece of the memory that is used to store things that get created over time as the program executes, okay? So just make it something very concrete. In Java, when you create an object, when you say new some object, okay, that object is going to be placed on the heap, right? In C++, when you create an object, or in C, when you do malloc, right? The malloc operation is an operation that creates a piece of memory for your program to use in the heap, right? So C has a particularity, and C++ has the particularity that the management of the heap is done by the programmer, right? So those of you who program in C and C++, you know that you are responsible as programmers to deallocate the memory that you allocate, right? So you create an object, and then sometime later on when you don't need it, you're supposed to deallocate it, to destroy that object, maybe free it from the heap, right? So that's a sort of a explicit garbage collection by the programmer. Many other languages have what's called automatic garbage collection. So one of them is Java. The modern languages all do, by the way. Java, Python, you name it. All of the modern languages have automatic garbage collection because it's a piece of technology and a set of techniques that people have gotten really good at. Okay, so it's now possible to do very high performance garbage collection these days. And so what Java and Python and all the modern languages do is that we allocate objects, and you don't need to worry about deallocating them. Okay, it's some other part of the virtual machine, it's called the garbage collector, that manages the heap and that is responsible for freeing up memory when it realizes that it's no longer needed. Okay, and the realization of when it's no longer needed, it can be many different techniques. All right, that's called the garbage collection. So this is basically the machine model that we have been using since the 40s. Well, not the stack. Okay, the stack came later. So if you ignore the stack, everything else has been there since the 40s. And then it comes in the 1960s, early 1960s, that's when the stack came around. And since then, this is pretty much, this models every virtual machine, if you want to call it like that, or every machine that, or physical machine that runs programs, okay? So the memory is important and the code is important, and the existence of this machine and this model is important also. Maybe, okay? For imperative programs, it definitely is important that you know all of these details, because imperative programming languages kind of force you to deal with this machine, with this model of the machine, even if what you're doing is, related to bank accounts and whatnot. The imperative programming style forces you to know about this. So memory management is very much sort of in your face in imperative programming, and thank God now there is automatic garbage collectors. So basically there's a stack. This is all stuff that I already talked about. So control flow. So I talked a lot about the memory. I talked about the stack memory is something that is necessary for the dynamic execution of the program, and the control flow, again, is something that is the dynamic execution of the program. And in imperative programming languages, control flow is designed to be sequential. So basically, that the instructions are executed in the order by which they are written. Okay, so you start at the top and you just continue until you reach perhaps a branching point or a looping point. So some condition, some condition is true, then you jump around. or case or a while or something like that, right? So when you reach these branching constructs that are also very typical of the imperative programming style, then it's not sequential anymore. You have these longer jumps, right? That you were here and now you just jump back to the beginning of the loop or something like that. And so branching originally, for example, in Fortran, in early Fortran, I don't know how many of you have programmed in low-level programming languages like assembly or something. It's you can see the low-level branching, which was that you had, you wrote programs that the programs, the instructions literally sat at specific addresses of the memory, okay? So for example, suppose that this is address number 10 and this is address number 50 and this is address number 90 or whatever. And so as you execute the instruction, if it's a branching instruction, like if conditional, then there was these go-tos, right? There was this go-to statement. Go to 50 means go to, make the program counter go to 50 and then continue from there. Okay, so this was the early form of branching that that's basically is what we have here is controlling the execution of the program at a very fine granularity, right? So we have the program in memory. So what we're going to do, thought the old people in the 40s, is to tell, okay, so now you jump down here and you continue from down here, and then down here I say jump back up, right? So because this is what I see, this is the machine that I see, this is the program that is laid down on the memory, and the different instructions are in different parts of the memory, and I know exactly what the addresses of the memory are. So this is what it meant to program. Okay? It meant also to control the flow of the execution entirely, down to very fine level of detail. And of course, this is what's called spaghetti code. This is what gave rise to the idea that at some point, so after this kind of programming went on, from the 40s and the 50s and even the 60s, this is what programming looked like. Okay? This is what, when people program, this is what they would be doing. Starting sometime in the 60s, people started questioning of the wisdom of doing things like that, because, it's kind of difficult. I don't know how many of you have done programming at this level. It can be fun, but it's super error prone, right? If you have people doing these kinds of manipulations, people are just going to do mistakes all the time. You jump to 50, and then instead of typing 50, you type 51, and there goes the whole thing. So or you change something, you add a variable, right? You add a variable in the beginning of the program, and now all the different instructions have shifted one or whatever. The labels have changed. So this is a big mess. And so in the 60s, actually, people started realizing that there was Aditya I'm sorry, Aditya, you had a question that I'm only seeing here. Isn't the heap managed by the OS in some cases? Yes, in some cases the heap is managed by the OS. And as usual in computer worlds, it's always an onion, right? It's almost, I hate to use this word, but it's almost sort of fractal, that you see the same structures at different levels. Okay, so you see the heap at the operating system level, because the operating system is also running some sort of programs, for scheduling processes and for doing file access and stuff like that. So the operating system is running programs too. But then there's also running programs at a different level. For example, if you start a Java virtual machine, that program is a program that runs Java programs, and so there's also the management of its own heap. Right? So you have this sort of fractal nature in as you see many times in computers. Sometimes you call it the onion, right? There's these little layers, and you see the same structures emerging in all these different layers because it's essentially doing the same thing. Okay, so I was talking about control flow and spaghetti code, and the fact that as in the 60s, the early 60s, people started to realize that after having written programs for 20 years that were sort of essentially very low level machine code, people started realizing that there was perhaps a better way by having these programming language. First of all, people started realizing that they were dealing with something called a programming language. Okay, somebody had to actually invent this term, programming language, because in the beginning, people that were doing these things, this was, you know, setting up the program, or, you know, there was no notion that there was something here that was actually creative and critical. But you know, after having experienced this, it was pretty clear that there was something creative and pretty important in the specification of the program itself, right? And the way that you specified it actually had different consequences in terms of number of bugs and stuff like that. So people started paying a lot of attention at being aware that there is a programming language that's actually important and interesting, and wanting to do different things and experiment with different programming languages. So it was a sort of an explosion of ideas in the 60s about programming languages, about how, you know, what kinds of programming languages you could do that had better, again, software engineering properties, even though they didn't have that word at the time. But so these long branches made it to C. Also, C is a much younger language, so C was developed during the 70s. But it still got those low level, some of the low level characteristics like Go2. But so somewhere in the 60s, also led by Dijkstra, by the way. Dijkstra was a very loudmouth, so if he would have a blog at the time, if there would be blogs at the time, Dijkstra would be a very popular blogger. He used to write a lot in what amounts to a lot of ranting about everything. So he was obviously a very famous computer scientist that you know, he invented this, or he invented the idea of using stacks for running programs. But then he went further and he started realizing, you know, he went on a rant again against what he called, sorry, against what he called unstructured programming. Unstructured programming was this idea of wild jumps, you know, arbitrary jumps to the middle of things. Okay, this is what programming was about, and he went on a rant against it. Okay, and the idea, his idea, it wasn't just him. Actually, it was a group of people that were designing languages, and they realized that there were certain styles that emerged from those years of experience of writing go-tos, certain patterns in there that started emerging, and it was pretty clear that those are patterns that people very often need. In particular, one of the patterns that was very often used, even if the language is very low level, was the pattern of having a subroutine, and then calling that subroutine from somewhere, and then wanting to go back exactly to where you called it from, rather than to some other arbitrary place. Okay, so they started realizing that there was some patterns, so there was some rules in the way that people were using these very unstructured constructs, like the long jumps, like the go-tos. In particular, the ones for calling a block and then coming back exactly to where you were, right? And that was sort of the beginning of people's awareness that you could perhaps have a layer of structure, okay, on top of a language that was completely unstructured. And that layer of structure was not to write the program, because you could write the program in a completely unstructured manner, but only and for the sole purpose of helping programmers, the people, right? Not the machine, because the machines couldn't care less, but the people, okay? The layer of helping the people, okay, write these programs that in a way that they would make fewer mistakes, right? So that was the beginning of this quest towards higher level programming languages. And that the goal is to help programmers make fewer mistakes. That's basically what it is, or write things faster too. So a group of people in the 60s started calling for what's called structured programming. And structured programming was a reaction against code like this, okay, against GoTos, okay. Basically, that was the reaction against GoTo. There was absolutely a rant by Dijkstra. That one I have linked from the page here. So Dijkstra, GoTo, he wrote a paper that you can read, GoTo Considered Harmful, which I should have been here in week 1. I don't know why I put it on week 2. And this, it's actually not a paper, it's a letter to the editor of the communications of ESM, just a 2-page letter, or even something very, very small. It's just a rant. It's quite funny to read this. It's just saying, basically, you know, GoTos are horrible. Everything bad in programming is because of GoTos, and they should be eliminated from the face of the earth. And so read the paper, kind of fun. So that was unstructured programming. So he and the group of people at the time wanted to move to a structured programming. So structured programming was a way to reign some order over GoTos. And right, okay, before I go, so Dijkstra wrote that little letter to the editor, GoTo statement considered harmful, which led, by the way, to a series of papers over the years, something considered harmful. They're all kind of imitating Dijkstra, that famous paper. But, you know, not everybody agreed with Dijkstra. In fact, another very famous old computer scientist, Donald Knuth, who's still alive, and he's still around Stanford. He actually wrote a counter argument to to Dijkstra rant with the title "Structured Programming with GoTo Statements." So he was a big fan of GoTos, and his argument was that guns don't kill people, people kill people, right? So it was not the problem of GoTos, it was the problem of certain programmers who did not know how to use GoTos properly. And if people knew how to use GoTos properly, then you could write beautiful code with GoTos that was much simpler, much more efficient, and stuff like that. You know, people have these kinds of discussions all the time about everything. So it's an interesting kind of dialogue that went on for a few years. There's also another paper, GoTo considered harmful to the N, or N is odd. So there was a series of papers, GoTo considered harmful. So another rank against the paper that Dijkstra had written. Anyway, so basically the general question is do syntactic rules force good programming style? Can they help? That was the question. You know, what can we do to help people program? Because it was pretty clear that people needed help at the time. And so structured programming is what we now have learned, what all languages now provide, right? All these higher level constructs, the if then else, for example, the while loops, the for, the case, all of that are the consequences of Dijkstra rant against the GoTos, okay? The reason why we don't have GoTos anymore is because they were kind of encapsulated or eclipsed inside this higher level branching constructs. They are still branching, right? But they are branching constructs with some regularities, right? Basically, the modern programming languages have removed our ability to freely send the program counter wherever we want it, right? So they have removed our liberty to shoot ourselves in the foot, okay? And instead they put these safety nets of higher structured constructs like the conditionals that we know, which underneath they are doing the long jumps, right? That's what they do when you transform that into lower level assembly language. That the branches are still there, the go-tos are still there, but it's not us who write the go-tos. It's the compiler. It's not us. So it's another program that knows what it's doing. It's written, those programs are written by people who are really, 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 really good programmers, and that's what that's the layer that does the transformation into lower level programming. So basically, this is all that we know, that we see in all the languages with these kinds of constructs, the conditionals, the looping constructs, the case, the switch statements. All that comes from the work, the political work from Dijkstra in the 60s against GoTo, and in favor of these higher constructs that survived all this time, until at least until functional programming comes around. But so this is what's called structured programming. So it's group code in logical blocks, and now we take this for granted. That's the thing that it's kind of hard to explain, because you all learn to program with these things. You don't know anything else, right? But you have to see this in the context of history, that before this, people were doing long jumps. Like programming was long jumping to different things, and that was very dangerous and very error prone. So this is a good thing that happened, and now we take it for granted. But we definitely, somebody had to invent it, and somebody had to make a sort of a political war against the other way of writing programs. So it cannot jump. So programs in structured programming, programs cannot jump into the middle of a block or a function body, right? It cannot do that in structured programming. So basically, structured programming came in to remove abilities that they were there, right? It disallowed us. They were constraints. They are constraints. We cannot do that anymore. Right? We cannot do that, and the language does not allow us to do it. In fact, going on a tangent here, the difference between the programming language and the library. Okay, so many of you use libraries, and perhaps libraries are what makes certain language ecosystems more valuable. The library ecosystem in Python is phenomenal, right? There's libraries to do everything we want. And so libraries can certainly help in when having things that are already there for us to do things, right? The difference between the language and the library is that the programming language actually is defined by its removal or its prohibition of doing certain things, more than its enabling of doing certain things, because enabling of doing something things can very easily be done with libraries. Okay, if you have some language and you want to do something else that the language doesn't do, you can call a library that does that for you and call the library. So adding new things is very easy to do with libraries, but removing things, disallowing, prohibiting things, you cannot do that with a library. So if you have some ideas for what is it that people should not do, okay, that you can only do with a programming language. That's sort of an interesting observation, that languages are actually defined by what they don't allow you to do. Okay, so here's another example. In modern languages like Java, C#, all the languages that have automatic garbage collection, they also disallowed us to do memory management. Like if you program in Java, you are not allowed to manage the memory. That has been removed from your purview. So, things that we used to do, to be able to do, we cannot do that anymore. And it's a good thing, because we don't need to worry about that anymore. It's a good thing. Sometimes not being able to do that, something is a good thing. I wish the NRA would also, somebody would shut down the NRA so that there was some little bit more ruling on the guns and stuff like that. anyway, I diverge here. So the structured programming is basically a set of rules, of constraints, of things that people could not do anymore. And some people were kind of resentful that they were being removed from some of those liberties. But that's for good and for bad, history, structured programming kind of won. For the reminder of the programming languages that came later, and they all kind of embraced the idea that you should not control the flow at that level of granularity because it's a bad idea. So this leads me to the assignment. So let me talk about the assignment, which is another thing that is very typical of imperative programming. And my goal now is to confuse you. I'm going to confuse you a little bit. Okay, and then hopefully that confusion will shed some lights over things that you didn't even thought they existed. So, everybody has seen assignments. You've seen them in almost all programming languages. They all look the same. X equals 3, X equals X minus 1. So it's formal. Set X to 3, set X to the value of Y plus 1, add 1 to X. So let's look at some examples, some other examples. So, so the first one, I equals, and then you have a condition there. If that condition is true, then I equals J, otherwise I equals K, that's fine. You also have M of I, which typically means some cell in an array, some position of an array equals to the value of some array, which index depends on some conditional. And then you have the third one, which is the weird one. And I'm gonna let you look into the third one, okay? Because the third one is weird, and I'm not sure that you have seen something like that. So the third one, it's you're assigning, but you don't really know what is it that you're assigning. Right? The thing that you are assigning is not clear. It depends on the conditional of whether A is greater than B. You assign M of J. Otherwise, you assign M of K. Some languages don't allow that. In fact, that is a weird thing. Like you don't know, you're assigning, but you don't know what you are assigning. But so what exactly is the assignment statement? Is it what can be on the left side and what can be on the right side? That's the question. Is just an expression equals to another expression? Is that what it is? Because that is really confusing. If it's something that an expression equals to another expression, then if you show this to some third grader that doesn't know how to program but knows a little bit of mathematics, assume that X is 5. Okay, so it's an expression, and you say X equals X plus 1. Does it mean that 5 equals 6? What does it mean, right? Okay, I want to confuse you because this is confusing, okay? We have been indoctrinated to kind of accept assignments as something that it's there, you just have to memorize what it means, but it can be very confusing. And in mathematical terms, actually it's super confusing. This is not the way that mathematicians use the equal sign, let me tell you. So what exactly does assignment mean? So it's actually not expression 1 on the left side and expression 2 on the right side at all. They might look like expressions, but they are not, okay? On the right side, it's actually an expression, okay? It's called an expression, something that you can evaluate. But on the left side is something else entirely. On the left side, that is supposed to be a location, okay? The location of some variable. That's what we are saying. So when we have an assignment, the left side is completely different from the right side. Okay, so the left side means the location value. It has to evaluate to a location in memory that then we are going to override, to assign, right? And so the right side is a regular expression, just an expression that you can evaluate to a value. Evaluate means that at the end you have a value. On the right side, however, it's supposed to be a location in memory that's where we're going to store that value. Okay, so the left side, it's called the location value, the L value, and the right side is called the regular value or the R value. Okay, and those are two subtly different things. They're not the same. And the reason that they're not the same, you see, for example, in examples, so on the right-hand side of an assignment, you use the variable R value. On the left-hand side, it's L value. So every variable has two things, okay? And X as a variable has two things. It has the value of X, and it has the location of X, where X is in memory, right? So it's the R value and the L value. So if you have X equals X plus 1, what this really means is get the R value of X, add 1, and then store the result into the L value of X, okay? So very specifically, this is what this means. And it took a while for people throughout this was actually very confusing in the beginning, how to make assignments and what exactly were the valid things on assignments. Until Strachey, a guy in programming that worked a lot in programming languages in the 60s. And he did a lot of work in the semantics of programming languages. Semantics means the meaning, okay? So he did a lot for clarifying the semantics of certain constructs, including the assignment construct. So L value and right value, this is concepts that he did not invent, but he wrote the paper describing that this was what was going on, okay? Because people were kind of pulling things off of their heads without really thinking much about what they were thinking. So an expression, here's a consequence. An expression that does not have a location value cannot appear on the left-hand side of an assignment, okay? So things like, for example, 1 equals X plus 1, you cannot do that. Why? Because 1 is a constant, it's not a variable. It does not have a location, okay? So if it does not have a location, then it cannot be on the left side. A of 1, however, can, because A is an array. So A is an array, there's a piece of memory that's array, and A of 1 is a particular cell of the array. And so there's a particular location in memory. So it has an L value and can be on the left-hand side. So these are subtleties of the assignment. So more subtleties. When a name is used in imperative locations in imperative style, when a name is used, it is bound to some memory location and becomes its identifier. Okay. The location can be in a global or in the heap or in stack, or it can be in many different parts of the memory. But it's basically there's a piece of memory, and the identifier identifies the location of that piece of memory. It's an alias, if you want, for that piece of memory, right? And the R value is the value that is stored at that piece of memory. So an assignment is a destructive update. That basically whatever was there, it's overwritten by the new value.
Excuse me.
Yep.
Shouldn't we consider an equivalent version of an instruction? For example, X++ is basically equivalent to X is equal, let X be equal with X plus 1. And in the previous slide, you said that, this X++ does not have the left-hand side, but, kind of as it is equivalent to, X equal with X plus 1.
So X equals X plus 1. Are you talking about X equals X plus 1?
No, I'm talking about X plus plus, which is equivalent to X is equal with X plus 1.
Expression? I'm having a hard time understanding what you are saying. It comes a little...
So my question was that, this, the instruction X++ is basically equivalent.
X plus.
Yes, exactly. X is equal with X plus 1, right? So
right. So, but you cannot have X++ on the left-hand side.
Okay, but it alone is an instruction, right? So
yeah, right. It cannot, however, you cannot do x plus plus equals 3.
Oh yes.
Or whatever, right? You cannot. It cannot be on the left-hand side.
Right.
That's what I meant, right?
Right. Okay.
Right. So the L value is the memory location, and the R value is the value stored at the memory location, and assignment is a destructive operation. Okay, that's what is going on. So any expression, assignment in imperative languages can be all understood in terms of L values and R values. Okay, thank God, now they can all be understood, because before Stretchy came and kind of sort of clarify these concepts for everybody, it was actually quite confusing for compiler, for language designers and compiler implementers about what is it that could be on the left-hand side. What exactly was that left-hand side? So, okay, so let me move on here. So this actually came in sequence of languages very much, you know, at the time that Stretchy wrote that a paper. So I don't know if do I link this paper for Stretchy? Yeah, I do actually. There's you know, there's a lot of papers that should be on week 1 and somehow on week 2 for some reason. So Stretchy's lectures on semantics of programming languages, pretty much semantics of assignments that he clarified, and this was in the late 60s, which then had an enormous influence on, for example, design of C. Okay, C started being designed in the 70s, and not just C, and before C, on the design of Pascal. Right, Pascal was another high-level structured language called structured language that also was the first one to have pointers. So pointers, the concept of a pointer as a concept in programming came from this clarification that there are values and there are locations, and that sometimes we want to manipulate values and sometimes we want to manipulate locations, okay? And the locations then is the concept of the pointers. The pointers are the locations. And so in C, you know, there's all sorts of details about how to denote the pointer, how to denote the content of the pointer, and how to, you know, the address of the variable, things like that. Okay, but I'm not going to teach you C right now. Copy versus reference semantics. This is something that has to do with, again, with locations and values. So copy semantics means that the expression is evaluated to a value, and then that value is copied to the target. So wherever you store the value itself. The reference semantics means that the expression is evaluated to some object, okay, whose pointer is copied to the target. So location is copied to the target. And this is used in object-oriented language. So let me give you an example. This may be too abstract. So when you, for example, in Java, when you pass an integer around, okay, you pass some method that receives an integer, when you pass the number 3, that is passed by value. It means that when you make that function call, there is a space on the stack that is big enough for an integer, and then when you call it, the number 3 gets placed there. Okay, it's called by value. Then there's also copy by reference in Java, for example. So an object, when you create an object, the object is stored on the heap, and what you get back is the location, is a reference to the object. And that reference is not exactly like the pointers in C. So pointers in C are actually direct memory addresses, okay? In Java and other languages, in Python too, the reference that you get is a wrapper around that location. There's more stuff in it. It's not just a direct location. It's a data structure that includes the location, but it includes more things, okay? And so that reference, then when you have a method that accepts an object of some type, when you pass it in Java, you pass just the reference, not the copy of the object. The object stays in the heap. There's only one copy of the object. What you pass around is the reference to that object, okay? There's a difference between copy semantics and reference semantics. What are you passing around? Are you passing a complete copy of the object, or are you passing just the reference to where the object is? Very important, a source of a lot of confusion for people starting to know how to program in certain languages. But let me explain to you what happens, for example, this is what I was talking in the beginning of this lecture about the slightly different meanings, okay, of the same thing in different languages. So in Java, C, C++, for example, you have x equals 1, x equals 3. What is really going on is a copy semantic. So you have the variable x that's supposed to be an integer, and you assign it to 1, then there's a location somewhere in memory, okay, that is bound to, that is denoted by x, okay, that x is basically an alias to a certain memory, and then it has a 1, and then it gets a 3, that memory, okay, that's what it means. For objects, so in Java, C++, Python, Ruby, when you have, for example, new objects, okay, x equals new foo, and then x equals new foo bar, you have, again, x, which is a reference, okay, it's an object reference. It's always the same size, an object reference. At one point, it has a reference to foo, and at another point, it has a reference to foo bar, okay, but it's the same location. That is the size of a reference, and that's what is going to basically overrides the R value of x2, but the value is a pointer or a reference of some sort, okay, a glorified pointer. Now, in Python and Ruby, it's slightly different. Python and Ruby are interesting because everything is an object. They are radically object-oriented languages, even more so than Java or Python or I'm sorry, Java or C++. So even constants are objects, even numbers are objects. So if you have x equals 1 and then you have x equals 3, it's actually a reference semantics. So the x first points to some object that is the constant 1, and then it points to another object that's the constant 3. Everything is an object. Every name that you have in Python is supposed to be just a reference to an object. That's all there is. Okay, they're just names that are bound to different objects at different points in time. So that is slightly different from Java and C++. All right, so typed variable declarations. The typed variable declarations restrict the values that the variable may assume during the program execution, and this you know from the typed languages like C++ and Java, that you actually declare the type of a variable. You have to declare it, okay? X is a double, or X is an integer, or X is some object of some sort. And it's important to know this for many reasons, not just to, for us programmers to know, but also for the compiler to know how much space it needs, right? It's also a compiler declaring the types of variables at compile time. When we write the program, the statically typed languages, the types are also convenient for the compilers because they can do all sorts of optimizations because you know how big things are. Okay, so how much space needed to doubles or to object references or whatever. So variables are pieces of memory that hold values of a certain type. That's what variables are. They are bound to names. Names don't have types, values do. And this is an interesting thing because Python, okay, or Perl or Ruby, they are not statically typed, right? So Python is not statically typed. It's dynamically typed. And what does that mean? It means that if you have x equals 1, and then later on you can have x equals hello, okay, a string, you can do that, okay? X is not of any particular type, it's just a name, okay? Names are not bound to types, okay? Because names are not variables, even though I bet that many of you, including myself, sometimes call these things variables in Python. right? If you have an X, you call it variable, that's actually technically incorrect. It's not a variable, it's just a name. A variable is a piece of memory that holds values of a certain type. That's what a variable is. And so statically typed languages have variables, but dynamically typed languages don't necessarily have variables. They just have names that are bound to values in different points of time, different points in time. So it's an interesting thing that you know, it looks the same, but actually there are slightly different semantics in different programming languages. Okay, let me see. Can I still do that? Assignment versus construction. I just go a little bit because this goes a little bit into the functional part. Assignment versus construction. So again, this is things that we use. We don't even think about it, but they have slightly different meanings. So here's an unconstrained use of an assignment. So you declare the variable X, you initialize it to 3, and this could be any language. It could be in Python too. Or here, this is Python. Here's the list, okay? You to empty and then you add something to the list, right? You have an iteration that actually changes the state of the list in a way, adds things to the list, right? Here's the exactly same thing, okay? On the right, you have exactly the same effect, but it's done in a slightly less imperative manner, and I'll tell you why. So this one, you also declare a variable, but at the point of declaration, you initialize it immediately, okay? So you give it an initial value. At construction time, you give it an initial value. That is okay. That could actually be not even a variable. If you don't change it, it's not a variable. It's only a variable if you change it, okay? So initializing things to certain values, actually that's what you should do. That's what everybody should do. Even in functional programming, you do that. You have to initialize things. But whether to change it or not during the program execution, that's where the difference is between imperative style and non-imperative style. So for example, for the list case, here's the same effect. You end up with things in the list, but in this case on the right, you do that at construction time. So it's at the time that you construct a list that you are immediately putting things on the list, not later on like we have here, okay? So that, you know, these little subtle, little details that you probably never stop to think. You would probably never notice unless I actually pointed to you. That there's actually an important semantic gap between, you know, this instruction that you created an empty list. That you're saying, I'm creating an empty list. And now you change your mind and you're actually adding things to the list. As opposed to the thing on the right that you're saying, I'm creating a list with these elements, okay? It has a very important semantic difference between one and the other. And one is more imperative because basically you're changing the state of the world, and one is less imperative because you're giving it an initial value and then that's it, okay? So whenever you can, please use, you know, give initial values to things and perhaps don't change them, okay? And that comes into functional programming. Okay, so I have another question from Aditya. Historically, why didn't the assignment borrow the assignment operator from mathematics and write it like, okay, we asked for initialization. That's a very good point. So it could have different syntax for initialization. Initialization is different from assignment. You know, some languages actually do that. Some languages distinguish between initialization and assignment, but a lot of the most popular languages don't do that, and unfortunately, because I think it's an important semantic difference. Yeah, it's probably due to language designers wanting to simplify the language, or maybe, you know, just people assuming that the assignment is okay and there's nothing wrong with assignment, and so let's just let people, you know, let's not make the difference between initialization and assignment. You know, that's certainly a difference that can be made, and definitely some languages do. So the problems with stateful code, and this is my last slide here, is that it's harder to trace than stateless code. And I'll talk a little bit more about that because, so the first thing is that, here's just a very simple thing. So you can already see that on the left, you have 2 instructions, or you have n instructions for something that it can be done in just 1. All right. And in fact, it's actually the difference is the semantic difference that I was saying, is that if your intention is to initialize something with certain values, then that's what you should write, right? That I'm initializing it to these values. That's something that you should be able to say. Whereas on the left, you are creating something without an initial value, and then you're changing it later on. Maybe the later on is immediately on the next line, but it doesn't matter, it's later on, okay? And so you are already setting yourself up to saying, I can change this anytime, kind of thing, okay? So this is harder to track than things that are never changed, okay? When you never change the values of things, it's much easier because you initialize it once and that you can rely that it will never change under you. And another thing that does not play well is with concurrency. Right, when you go, and I'll have a week here dedicated to concurrency. When you go into concurrency, we have threads, and you start changing the state, and you start having threads sharing the state that each one can change independently. That can be a mess very, very quickly. It can generate the most gigantic mess of your life, and all sorts of race conditions, and so. Stateful code can be harmful, okay? Stateful code can be difficult to manage. And it is my experience that if you can do things that in a way that is stateless, you should always strive to do it because it will make your life a little easier. But this is a theme that is going to evolve over the course. Okay, it's already 8:20. I spent the entire lecture talking about imperative style and going a little bit into the next week's topic, which is functions.